So without a graph, the first set of directions, are asking you to state the domain. So remember, when we're looking at an equation and they're wanting us to know about the domain, or they're wanting us to state the domain, we look for two things. We look for variables where? In the denominator, okay? Doesn't matter about variables in the numerator, but we know that our denominator can never go to what? 0. Our denominator can't be 0 because if it is, our function is undefined and it's no good for us, no use for us. So when they're talking about the domain of an equation, we're looking for any variable in the denominator that makes the denominator go to 0, and we're also looking for any variables that happen to be underneath what? Square roots. Okay, y'all see any square roots on number 2, 4, 6, and 8? None at all. So we don't have to worry about the square root part. So we're just looking for any variable that's in the denominator and what value of that variable would make the denominator go to 0. So number 2, there's an x in the bottom. What can x not be? X cannot be 8. So you can write x does not equal 8, or you can just think that. So if our domain can be everything except 8, do y'all remember how to write it? We do parentheses, negative, infinity all the way to 8. We say that we can't have an 8 by using what symbol? Parentheses. The bracket means 8 is included. The parentheses just means we go all the way up to 8, 7.99999. Then we have a union symbol. Then we have another parentheses. And then we say our domain continues from 8 to positive infinity parentheses. We're always using parentheses on infinity because infinity is a number that we can never reach. We're just always approaching that. Everybody remember how to do this? Okay, so they're going to go back and start with some equations, some things that you've already done. Then we're going to jump into some graphs, and we're going to look at domain again. And then tomorrow we're really going to start graphing those equations that we're looking at, 2, 4, 6, and 8. We've never graphed anything like that before. That's a new graph for you. That's called a rational function because it's got some x's in the denominator. In number 4, the denominator's factored for you. That was nice of them. There are two values that x cannot be. What are they? 2 and negative 6. Okay, if you need to write that down, x cannot be 2 or negative 6, you can write it down. But this time, there's two values for x that x cannot be. So we're going to have to go negative infinity to the smallest excluded value, which is negative 6 parentheses, union, and then you'll do negative 6 to the larger excluded value, which is positive 2 parentheses, union, and then finally parentheses 2 to infinity. So when you have two excluded values, you'll have 3 interval notations with the little union signs in between the interval notations. If you just have one excluded value, you'll have 2 interval notations, and when we get to the graphs, hopefully it'll make a little bit more sense. So in example 6, the denominator is not factored, but you can factor x squared minus 64 how? It's called the difference of squares. And how does x squared minus 64 factor? X plus 8 and x minus 8. Again, we care nothing about the numerator. X's can be in the numerator, x's can be 0. The whole entire numerator can be 0, but the denominator can't be. So we're just looking at the denominator only. So there's two excluded values. What are they? Negative 8 and positive 8. So the answer to number 6 is going to look very similar to 4. So we're going to go negative infinity for our domain up to our smallest excluded value, which is negative 8 parentheses union. In the middle, what would the interval be? Negative 8 to positive 8 parentheses union, and then finally our biggest interval, our largest numbers, will be positive 8 to infinity. Again, the directions say find the domain of each rational function. A rational function is just an equation that has an x in the denominator. All right, for number 8, a lot of people are going to miss number 8 because they're going to think there is an excluded value, but there can't be an excluded value for number 8 because if you have an x and you square it, no matter whether it's negative, positive, or 0, and you add it to 64, you're never going to get a 0 in the denominator. X squared plus 64. No, negative squared plus 64 will give you 0. No, positive squared plus 64 will give you 0. 0 squared plus 64 will not give you 0. X squared plus 64 will not factor because it's not the difference of squares, it is the sum of squares. So there's no excluded values in number 8, so we say the domain is negative infinity to positive infinity. All right, any questions about those 4? All right, next set of directions are going to give you a graph. Okay, what we're leading up to tomorrow, we're actually going to do the graph. Okay, we're going to do our own graph, and all the graphs will look similar to this one, but right now we're not ready for that yet. You're not going to have to graph tonight, but they will give you graphs, and they're going to ask you some questions about your graph. It says, use the graph of the rational function in the figure shown to complete each statement in 9 through 14. And on the graph, this is the part that I thought you might not be able to read. Up in the left-hand corner, it says vertical asymptote at x is equal to -3. There is a vertical asymptote. So vertical asymptote goes up and down. You see the dashed line at -3. My graph can't cross that line, okay? Sometimes, it's really rare, sometimes a graph might cross an asymptote. Y'all remember having asymptotes in hyperbolas where you drew the rectangle and then you drew the diagonals? Those diagonals were asymptotes. Remember, our graph just approached the asymptotes, and that's what an asymptote is. It's some type of line where the graph approaches it, but it usually never touches it. If it does touch it, it'll cross it quickly and follow it on the other side. So we have a vertical asymptote at x equals -3. We have a horizontal asymptote at y equals 0. Which axis is y equals 0? The x-axis is where y is equal to 0. And then we have another vertical asymptote at x is equal to 1. Another dotted line going up and down. That's a vertical asymptote that our graph is going to approach. We need to know that information. Again, you're going to get to graph these equations tomorrow, but they're going to just ask us some questions. So for number 10, the problem says, and this is brand new little notation here, it looks like calculus, but it's not. Number 10, it says as x approaches, that's what the arrow means, as x approaches -3 from the right. So the little bitty plus sign that's in the exponent spot, that means from the right. The negative means from the left, okay? So as your graph, as the x's approach -3 from the right. So this is what it would look like. So your graph is coming in, it's approaching -3 from the right. So I'm coming in from the right-hand side, so I'm talking about this piece of the graph. So first thing that you have to understand what this notation is saying. As x approaches -3 from the right. So we're coming in from the right. We would stop here if we were approaching 1, and we would be talking about this piece. But it says as we're approaching -3 from the right-hand side. This is the right, this is the left. So as we're approaching, x is approaching -3 from the right, what is f of x or y approaching? What are your y's doing right here? What value are they approaching? Infinity. And this is so easy for some people and so hard for others. So we'll just kind of take it slow. We're just doing the evens here. So number 10 says, as your x's approach -3 from the right-hand side, f of x, which is your y values, is approaching positive infinity. Let's look at number 12. 12 says, as x approaches what? 1 from the right. So as x approaches 1 from the right, so we're approaching from the right, we're approaching x is 1, and this is the piece of the graph that we're talking about that's approaching 1. What is f of x approaching? Positive infinity. It's not going to always be positive infinity, but those two are. All right, number 14 says, as x approaches positive infinity. Now, when you do positive and negative infinity, you don't have to say from the left or the right, because if you're approaching infinity, you're approaching from the left. If you're approaching positive infinity, you're approaching from the left. If you're approaching negative infinity, you're approaching from the right. So they don't have to put the little symbol here. Okay? So 14, as x approaches positive infinity, okay? So that means you're coming this way, your graph's approaching positive infinity on the x's, then we're on this piece. This is the piece that's approaching positive infinity. What are the y's approaching here? 0. I want you to think about that. As the x's approach positive infinity, okay, as the x's approach positive infinity, you're on this piece of the graph. You're on this piece of the graph right here. As the x's are approaching positive infinity, they get to 100, and then they get to 1,000, and then they get to 10,000, then they get to 1,000,000. Since it says we have a horizontal asymptote at y equals 0, then that piece of the graph is just approaching the x-axis. So that means that your y values are approaching 0 there. That arrow is not going straight down. If it were going straight down, then the f of x would be approaching negative infinity. If it were going straight up, then the x's would be approaching positive infinity. But it's not. It's leveling off where all the y's are equal to 0. It's leveling off there. All right, can y'all think of anything to ask about 10, 12, or 14? These will just be fill in the blanks. You don't have to write the problem, but you have to think about what it's asking you in order to get the answer. Yes? The little plus sign means you're coming from the right of the graph. You're approaching the number from the right if you have a little plus sign. If you have a little negative sign there, then you're approaching that number from the left. Okay, anybody else? All right, they're going to change graphs on you. So in around your graph, it's going to tell you about some asymptotes. Down here it says we have a vertical asymptote at x is equal to -2. Here it says we have a vertical asymptote at x is equal to +1. Those are going to be those dotted lines that your graph is going to approach. Sometimes the graph crosses there, but if it crosses, it'll continue to approach it on the other side. And then I don't have a horizontal asymptote at y equals 0 this time. I have a horizontal asymptote at y equals 1. That's why you see that dotted line up 1. Okay? Now I'm going to highlight the asymptotes for you because this will be the first thing that I teach you tomorrow. Is I'm going to teach you how to find vertical asymptotes. I'm just going to highlight the vertical asymptotes. I'm going to teach you how to find vertical asymptotes tomorrow. And I'm going to teach you how to find horizontal asymptotes tomorrow. So I'm just going to kind of highlight those. Asymptotes are lines that your graph approaches. Sometimes it crosses. Okay, if it does cross, then it will approach it on the other side. So let's look at number 16. So 16 says, as x approaches 1 from the... Number 16, as x approaches 1 from the left. Number 16, as x approaches 1 from the left. So that means you're coming from the left. So you're approaching 1 from the left. You're approaching 1 from the left, and you got to get on your graph. So if we're approaching 1 from the left, we're on this piece of the graph right here. This is the piece of the graph that's approaching 1 from the left. What's the f of x values doing here? They're approaching negative infinity because the graph's going straight down there. So think about that. As your graph, as the x's approach +1 from the left, f of x is approaching negative infinity. Number 18, as x approaches -2 from the left. As x approaches -2 from the left. That means we are talking about this piece. As x approaches negative 2 from the left. Talking about that piece I just highlighted in red. As x approaches negative 2 from the left, what are the f of x values approaching? The bottom of the graph is not approaching negative 2 from the left. Okay, if you're thinking about this piece, it's approaching negative 2 from the right. Okay, so you got to make sure you're on the right piece of the graph. This piece of the graph is approaching negative 2 from the left. This one is approaching negative 2 from the right. This piece is on the right-hand side. This piece is on the left-hand side. So that arrow is pointing straight up. So the y's, or the f of x values, are approaching positive infinity. Number 20, as your x's approach negative infinity. So if they use negative or positive infinity, they're not going to say from the left or from the right. So if your graph is approaching negative infinity, then we're talking about this piece over here that I'm highlighting in red. This is the only piece of the graph that is approaching negative infinity. Okay? That's the only piece that's approaching negative infinity. And is that piece pointing straight up or straight down? No. So it's approaching that blue horizontal line, which has y values of 1. So as x approaches negative infinity, your f of x, or your y values on the graph, are approaching the y value of 1.
So would you explain what you would do if you're approaching
Positive infinity? If you're approaching positive infinity, then you would be on this piece. And I'm going to have to erase let me erase this highlighting here, just so you can see it. If your graph was approaching positive infinity, you would be on this piece. Okay? And what would y be approaching on that piece that I just highlighted? Would it be pointing straight up? Nope. Straight down? Nope. It's leveling off, and it's leveling off where y is equal to what? 1. So on this particular graph, as the graph goes to negative infinity and positive infinity, f of x approaches 1.
So it doesn't matter that
No, what's going to happen is it's going to cross that dotted line, that horizontal asymptote, and it's going to follow it on the other side. Rational functions are followers. They follow asymptotes. They don't usually cross, but the longer I teach, the more random problems I find where that we do find a graph that's going to cross the asymptote. If it does cross the asymptote, then it's just going to follow it on the opposite side. So instead of following it on the top, it's going to continue to follow it on the bottom. Okay? Next set of directions, or last set of directions, are going to say find the vertical asymptotes, if any, of your graph. So we're going to do a little bit of the vertical asymptotes in tonight's homework. We'll go back over vertical asymptotes, and then tomorrow I'm going to show you how to find horizontal asymptotes. And then once we know how to find our vertical asymptotes and our horizontal asymptotes, we'll be ready to graph rational functions. And that's what we'll do tomorrow in class. We'll actually do the graphing. Sorry, trying to move these evens up. All right, so you might want to write this somewhere. Vertical asymptotes. Vertical asymptotes. I'm going to abbreviate. Come from excluded values in the denominator. Vertical asymptotes come from excluded values in the denominator. Vertical asymptotes come from excluded values in your denominator. Horizontal asymptotes follow a set of rules, or 3 rules for horizontal asymptotes. Vertical asymptotes are easier to find because you're just looking for excluded values. So in number 22, what can x not be? 3. So that means I have a vertical asymptote at x is equal to 3. So if I had to graph number 22, I would go to the right 3 from the origin, and I would have a vertical dashed line at x equals 3, because at x equals 3, this function is undefined, and your graph would approach the vertical asymptote x equals 3. And number 24, there are 2 excluded values. What's the first one? 0. That first little x all by itself, it can't be 0. So you have x equals 0, and you also have a second vertical asymptote at x is equal to 3. So vertical asymptotes, you're used to finding excluded values. That's where they come from. So you would have a dashed line where all the x's are 0 on your graph. You'll have another dashed line, vertical line, where x is equal to 3, and that would split your graph up into 3 pieces, and then your graph just approaches the line x equals 0 and approaches the line x equals 3. Alright, so 26 looks almost exactly like 24. Who can see the difference? There's no plus 3. Okay, that's true. Anybody else see something that's going to happen in 26 because there's not a plus 3, Mary Frances? The x's will cancel here. Okay? If your x's cancel, then that x in the bottom is not going to give you a vertical asymptote. It's actually going to give you a hole in your graph. Okay? When the x is canceled, that's where the graph is going to give you a hole. It'll just be a little open circle in your graph. When you get to calculus, those are called points of discontinuity. You'll learn all about that in calculus. So the x's are going to cancel there. That means there's a hole in your graph, but they're not asking us about holes. They're just asking us about vertical asymptotes. So then you just look at the x minus 3. So there'll only be one vertical asymptote, and that'll be at x is equal to 3. Because x can't be 3, okay? X can also not be 0, but that x canceled out. You wouldn't have a vertical asymptote at 0 on number 26. All right, and last one, 28. X over x squared plus 3. The x and the x squared can't cancel in 28 because that's x squared plus 3 is a binomial, so it's like a little family, and you can't divide or cancel the x in the top with the x squared in the bottom. What excluded values do you see in the denominator? X squared plus 3. That's a trick question. There's no excluded values when you have x squared plus a number. There's nothing that you can square and add to 3 that gives you 0. Nothing that you can square and add to 3 that gives you 0. Okay, so that's why the directions say find the vertical asymptotes if any. And there are none for number 28. None for number 28.